What's going on, everybody? It's Mr. Gust, and I'm back in the physics classroom. I want to talk today about drawing force diagrams. We've drawn a lot of force diagrams so far, including in Unit 1, but those diagrams were pretty straightforward. They basically were only objects in free fall, only objects that were being acted upon by gravity, and gravity is super straightforward. It always acts downward towards the middle of the Earth or whatever planet you're on. So this time around, we're going to have different forces being acted on things, right? So let's take this for example. This is an object that is being pushed. This object is being pushed across the surface at a constant velocity. That's what this object is. Okay, so it's sitting here, it's being pushed across the floor at a constant velocity. We can even go ahead and kind of label that and say, like, hey, this is the direction of velocity. This is how I might draw this picture. But I'm not asking you really to draw the velocity vector. I'm really asking you to draw the force diagram. We call these FBDs. They stand for force body diagrams or free body diagrams, depending on who you ask and how old they are. All right? But basically, it's just a model of the forces. And there's convention to this, right? The world of physics is full of convention. Are there more than one or is there more than one way to do something in physics? Of course, but there are conventions that we try to follow in physics because then we can communicate between classes. Shoot, we can communicate between schools, even communicate internationally if we follow these conventions. So we're going to follow these conventions, okay? So first things first, let's look at this image. The first thing I'm going to do is identify my object in this scenario, and done. There's my object. I've identified it. It's right there. Okay? I want to represent that object with a dot. This convention is take it or leave it. You can, you don't have to, but I'm going to go ahead and say, here's my object. I'm going to put the dot right in the middle of my picture and say, hey, that's the object. That's the center of mass of my object. That's the object. Draw in the surface touching with a dashed line. I can see the object. I'm drawing on the picture. I can go ahead and see that there's a surface right there. It's touching my object. I'm not going to draw that. But some people will ask you to do that. I'm not going to. Now it says represent all the forces acting on the object using vectors, using arrows. This is where my physics brain and my human brain have to kick in. I have to think about what are the forces that are acting on this object. I really need to read my problem and understand the world I'm in. So first things first, this object is on the planet Earth, so I'm going to go ahead and draw gravity. Gravity pulls straight down on my object like this. Got it. Is this object accelerating up or down? I ask myself this question because if it's not accelerating downward with gravity, there must be some other force pushing back on it. Well, this ground is in the way. The ground is not allowing this object to go into free fall, so the ground must be pushing up on this box as well. And we have a fancy name for these ground forces. We call them normal forces. And normal is a word that quite literally in mathematics means 90 degrees, or it means perpendicular. So perpendicular to a surface would be a normal force. If there's a surface and an object touches that surface, there's a force on the normal to that surface, normal force. This is what it is. It's perpendicular to the surface. Gravity pulls down, pushes the box into the surface. The surface supports the box, pushing it straight back up normal to its surface. Okay? Asking myself now, if this box is not accelerating up or down, the net force or the acceleration is zero. Therefore, my net force acting on this object must be zero. So I'm going to say that these forces are not only in opposite directions, but they're balanced. They are balanced because there's no acceleration up or down in this case. All right? So I'm going to balance those forces out, and I'll draw some congruency marks to make sure that they're balanced. Let's look at the other direction, because it says the box is pushed across a surface at a constant velocity. Again, no acceleration, but it's pushed, and it's pushed to the right. So I'm going to go ahead and draw that push force. F push. There it is. If this box were accelerating across the floor, that would be the only force acting in the horizontal direction. But it's not. It's moving at a constant velocity. Constant velocity indicates no acceleration. If there's no acceleration, there must be no net force, no total force. If there's no total force, there must be something preventing this box from accelerating. Now, again, using our human brain, if I push something across the floor, I can actually hear the force that's pushing back on the box. I'm pushing something across the floor. I'm going to hear friction. I'm going to hear that rubbing, that force. This here is the force of friction. It's preventing the motion across the floor. And because there's no net force, because there's no acceleration, these two forces, they must be equal to each other because there's no acceleration. I feel like I keep saying this. All right? So I've represented all forces on the object using vectors. I've drawn them from the dot. The arrows or the length of the arrows represent the size of the force. I wasn't really given information about the size of these forces, but I do know that they're congruent, so I drew the arrows that were congruent or the same magnitude. I drew those arrows the same size. Lastly, it says break vectors in x and y components. I don't really have that. I've got these vectors that are going horizontally. I've got these vectors going vertically. I'll show you an example next of when I have vector forces or component forces, but right now they're in the same direction. Lastly, it says write a net force equation for the x and y direction. So not only is net force total force, net force has direction as well. So I'm going to have horizontal net forces, and I'm going to have vertical net forces, okay? Net force just means total force in the x direction and total force in the y direction. So if I go ahead and do this, F net is going to be equal to MA, and this will be in the x direction. This will be MA in the y direction. These are the, again, directions. So this is my equation, but what makes up these net forces? What forces are in the vertical direction or the horizontal direction? Let's start with F net x. F net x has a push force. That's one force. I can look at my diagram. I see there's a push force. F push. It's going to the right. I also have a friction force. The question is, are these forces being added together or are they subtracting from each other? Is the push force and the friction force causing things to accelerate more and more, or are they working in opposite directions? Because vectors have direction. Well, the push force is to the right, and since the friction force is to the left, I have to give it the opposite sign of the push force. Push and friction are opposite directions. They must have opposite signages in the equation. This here is my F net expression for the x direction. M times A equals the sum of all of my forces. One force going to the right minus one force going back the other direction. Let's look at the vertical direction. The first force I notice is my weight force or gravity. Gravity's pulling downward, but I can still call that positive. It doesn't matter which way I call positive or negative as long as I know that opposite directions have opposite signs. Is there any other force vertically? You betcha. There's this normal force, this 90 degree from the surface force. This force is acting in the opposite direction to gravity. So I make sure it has an opposite sign. This here is my F net in the y direction. Okay, now I know that the accelerations in both cases are 0, so Fg minus F normal is 0. Fg equals Fn. F push equals force of friction because there's no acceleration. I know this from this picture. This is fantastic. Everything works out, but this is how I draw force models and then write F net equations from there. And again, this one's not accelerating. It makes things a little bit easier in terms of what they're equal to in their congruency marks, but this is how I do it. Let's try another example. I want to see one that maybe has some components to it. So here's another one. I've got this image. It's a box held up by two strings, not on a surface, but by two strings. Let's go ahead and sketch our forces first. So here's my dot that represents my object. It's on Earth. There's the force of gravity pulling it down. There's no surface to support it. There's only these strings. And so these strings are actually going to pull at an angle. Strings provide what's called a tension force, where there's a force pulled through that string, okay? And so I see two tension forces. These two strings are supporting the weight of that box. Now, none of these are congruent with each other. Maybe the two tensions are, but I'm not certain. But here's the problem. If I go ahead and think about the forces in my x direction and the forces in my y direction, when I do this, I don't really have anything like perfectly vertical to support gravity. And I don't have anything perfectly horizontal. These two strings are acting both vertically and horizontally. So what that means is I actually have components. I've got components of tension forces acting a little bit vertical and a little bit horizontal. So just like we did when we launched things at angles, I'm going to have to examine what this tension force in the x direction is and what this tension force in the y direction is. And I'm going to have to do that for both. So I'm going to call these FTY1 and 1 and FTX2 and FTY2. Because I have tension force on the left, I call that tension force 1, and I can call this over here tension force 2. Okay? So now that I've done this, I see that there are components of these forces. So if I go ahead and now write out my FTX, or my F net x, I'm going to look for the x direction. And I know this thing's not accelerating, so mass times A is 0, but there's F tension in the x1, opposite direction, pulling the other way is FTX2. These two forces are pulling in opposite directions. One's left and one is right. And when I think about FTY, I know that there's gravity, or F net y. There's gravity, but then pulling upward of gravity would be FTY1, and then in the same direction as tension 1, so also negative, FTY2. Why is it negative? It's negative because it's opposite the direction of gravity. Gravity I called positive because it was first. These two I'm calling negative because it's opposite. Not that it matters, but I could change the signs easily, make gravity negative and make these two positive, whatever you want, okay? So these are my expressions, but I'm not going to leave them as FTX1 and FTY2. I can actually go a little bit deeper. I can actually plug in some things. So if I look at these triangles where I have FTY1 and FTX1, and here's my tension force. This is a right triangle. So I can actually substitute in my vectors, my sines and cosines. So in this case, FTY is going to be equal to the sine, or FTY over FT is equal to sine theta, because it's opposite over hypotenuse. And FTX is going to be equal to, FTX over FT is equal to cosine of theta. Very similar to what we saw with our velocity vectors. And I can actually make these substitutions around and say, you know what, FTX is actually the tension force times cosine of theta. And FTY is actually equal to FT times sine of theta. I can make these substitutions into my expressions down here, and that's exactly what I want you to do. It's what I told you earlier. Make sure you include components. So MAX is actually equal to FT1 times cosine of theta minus FT2 cosine of theta. And down here, we have MA in the y direction, which is 0, is equal to FG minus FT1 sine theta for my y direction minus FT2 sine theta for my other y direction. Now again, these are equal to 0. The accelerations are equal to 0 because it's not moving or it's at a constant velocity. So I'm not going to have to do any math here. But if it did have an acceleration, I could plug in mass, acceleration, and start solving for some things. This is just the basic convention for drawing force models, for writing F net expressions from those force models. And hopefully this becomes helpful for you as we start to do more advanced mathematics and solving for different variables in this way. Okay? See ya!